Hi, today's lesson is on polar or nonpolar molecules. How do I determine if something is polar or nonpolar? So we're going to look at two molecules, water, which I've drawn here already, which is polar, carbon dioxide, which I've drawn here, is nonpolar. And this is very important because if water was not polar, then there would be no life on Earth. Why do I say that? Because its polarity gives it its strong attraction, which makes it a liquid at room temperature, which gives us oceans and streams. And scientists still believe we need liquid water for life. So without water being a liquid, it would be a gas if it was nonpolar, we would have no life on Earth. So how do I tell that water's polar and carbon dioxide, which is a gas, is nonpolar? Well, let's follow some rules. First of all, we have to realize what polar is. Polar means opposite. So I have to have one part of the molecule that has an opposite charge as the other side. So one side has to be a little negative and one side has to be a little positive. And to have that, I need at least one polar bond in the molecule itself. So what is a polar bond compared to a polar molecule? Well, the bond has to have one side of the bond be a little negative and one side be a little positive. How do I get that? I get that from unequal sharing. So hopefully you remember that from previous unit. Unequal sharing is a polar bond. How do I get unequal sharing? That comes because I have different pull on those electrons, which is based on their electronegativities. So you may need to take out Appendix A4, which is the electronegativity value, and follow along with me. If the difference in their electronegativities is 0.5 or greater, then the pull is different enough to create one side of the bond being negative and one side being positive. And I should say being partially positive and partially negative. So let's go back to this and see what kind of bonds I have. I have an O to an H bond, and another O to an H bond, and here I have a C to an O bond and a C to an O bond. Sometimes you have different bonds. In this case, I have the same bond on each side of the molecule. So hydrogen happens to have an electronegativity of 2.1, and oxygen has an electronegativity of 3.5. So the difference, the change in electronegativities, is 1.4. So this is a polar bond, and this is a polar bond. What about carbon oxygen? Well, carbon is 2.5, and I wrote down oxygen is 3.5. So the difference in electronegativity is 1, which is greater than 0.5 or 0.5 or greater. So this is a polar bond, and this is a polar bond. All right, so I meet the first criteria, at least one polar bond. But I've already told you that this one is polar and this one is nonpolar. So it has more to do than the bonds themselves. It also matters the shape of the molecule. So the shapes of molecules matter for several reasons, and their polarity is one of them. So let's give a little bit more room now that we know that they're polar, nonpolar. So let's go back and try to figure out these shapes and why one shape makes it polar and one shape makes it nonpolar. So water has 1, 2, 3, 4 groups of electrons. So it is a molecule. So hopefully you remember doing that from the previous studies. And carbon dioxide only has 2 groups of electrons, which gives it a generic shape of 180 degrees. And water's generic shape is 109 degrees, approximately. And so this is a linear molecule. Now you might remember from what we just said, polar has to be opposite. So I have to have one side different than the other side. Well, if you look at carbon dioxide, it is linear. One side is the same as the other side. What about water? Well, water, the left and the right side are the same. So water, the left and the right side are the same, but the top and the bottom are not the same. So the top can be partially negative, which it is, and the bottom can be partially positive. So how do I decide which side is a little negative or which side is positive? The one that has the bigger electronegativity pulls the electrons closer, and that's going to be your negative side. So what matters about the shape? It's something we call symmetry. So if a molecule is symmetric, one side is the same as the other. If it's asymmetric, which is not symmetrical, then one side is different from the other. And you have to be careful because water is, well, that's kind of a bad drawing of water. Water is symmetrical left to right, but it is not symmetrical top to bottom. And if you really looked at the true definitions of polarity, it would go into something about vectors and adding the vectors together. We're going to make it a little bit simpler than that and just look at the overall symmetry of the molecule. And you say, what, Miss Backus, I'm having difficulty not seeing that this is asymmetric. It kind of looks symmetric to me. Well, I'm going to give you some clues at judging symmetry. So let's move down here. How do I tell if something is symmetrical or not? Well, if it's bent or if it's a pyramid, it is never symmetrical. Why? Because these shapes, the tops of these shapes are different than the bottoms of these shapes, right? So something that is bent looks like this. The top is different from the bottom. If something is a pyramid, it looks like this. The top is different than the bottom. They are never symmetrical. What about the other shapes? Can they be symmetrical? Well, sometimes they are and sometimes they're not. When are they symmetrical and when are they not symmetrical? Well, linears are symmetrical if the ends are the same. Carbon dioxide has oxygen on both ends. It is symmetrical. Tetrahedrons are symmetrical if the ends are the same, and trigoplanars are symmetrical if the ends are the same. So, let's go back to our rules. So something is polar if it has at least one polar bond. We just described that. And it has to be asymmetrical, which is not symmetrical. Oops, two M's. Let's forget that. So let's go back to our example. Water has at least one polar bond. There's a polar bond here and a polar bond here. And it is asymmetrical. It is bent. Bent shapes are never symmetrical. Their tops are different from the bottoms. Carbon dioxide has a polar bond, but it's symmetrical. The top, if I split it in half this way, the top and the bottom are the same. The left and the right are the same. So I can't have one side that's a little negative and one side that's a little positive because they're not different. They're not polar. So to be polar, I have to have at least one polar bond and asymmetry. To be nonpolar, I have to have no polar bonds or, notice I use the word or. I don't have to have both, just or symmetrical. I could have both, but I don't need both. Either I have no polar bonds or I'm symmetrical and I'm still a nonpolar molecule. So let's try some examples of this and see if we can figure out. So CH2O is this molecule right here. I already did the Lewis dot for it. It has 1, 2, 3 groups of electrons. And so this has this generic shape. It's flat, it's planar. I have a carbon here, a hydrogen here, a double bond to oxygen here. That's trigonal planar. It is not symmetrical. This side, this right side is different from the left side. It's not because these ends are different. So it's not symmetrical. But is it polar? To be polar, I also have to have a polar bond. So I have to look at the bonds. I have a C to an H bond here and here. But I also have a C to an O bond. And it doesn't matter if it's single or double. It's just a C to an O bond. So C is 2.5 and H is 2.1. So the difference is 0.4. That is not a polar bond. C is 2.5 and oxygen is 3.5, so the difference is 1. So this is a polar bond. So I have a one polar bond, asymmetry, CH2 is polar. CH2O is polar. What about this other example? I have SiF4. This time I drew a structural formula. And the structural formula shows me that I have 4 groups of electrons. This makes this a pyramid shape. Now, pyramid shapes are symmetrical if all the ends are the same. All the ends are the same. So if I really did a vector diagram of the different poles of the electrons, they would all cancel out and have a net of 0. So this is symmetrical. Well, out of curiosity, I could stop there because I now know it's nonpolar. Why? Because I don't have to have both. I have symmetry, so I don't even have to look at the polar bonds, but I'm just going for the fun of it, because aren't we having fun? So Si is 1.8 and F is 4.0. So the difference is 2.2. And so these are polar bonds, but it is not a polar molecule because it is symmetrical. One side is not different than the other side. So give these a try with your homework. If you have questions, ask in class, and thanks for listening.